Happy Monday. Only 2 weeks left of classes. Isn't that sad? I want to continue talking about these conjugated systems. And when we left on Friday, we were talking about this reaction, the Diels-Alder reaction, which is one of the main reactions of conjugated dienes, and a very powerful one for building organic molecules, because it has a lot of features to it that provide us handles to control a lot of the aspects of the reactions. So today, we're going to spend some time discussing the details of this reaction, the way in which it is controlled, some of the factors which lead into its ability to be able to do very selective formations of cyclohexene products. So remember what we were talking about on Friday. The Diels-Alder reaction combines a diene that's conjugated with another double bond. So overall, a 6-atom process, combining 3 pi bonds in total, 2 from the diene, 1 from our dienophile, and the reaction occurs all in one step to form a cyclohexene. So notice we've sacrificed pi bonds now for carbon-carbon single bonds, or sigma bonds. Many different kinds of groups participate in this Diels-Alder reaction, but in general, the reaction works best if the diene is electron-rich and the dienophile, that is the double bond reacting, is electron-poor. So that's the best pairing for these two reacting partners. If they're both completely neutral, then it can work, but it generally is a higher activation energy barrier. And I'll explain a little bit. I want to cover a little bit of the explanation for why this is the case. And look closely at when we look at the pi molecular orbitals, or how the orbitals actually interact, because that's really the way that this is controlled. So you'll notice a lot of the various groups I have here on these examples. Okay, I have a double bond which has an ester functionality, so a CO2CH3, that's abbreviated here, or a nitrile, a CN triple bond. Okay, all these are electron withdrawing groups. They help to decrease the electron density in the pi system that's undergoing the reaction of the dienophile. They can be cyclic. Maleic anhydride actually has 2 electron withdrawing groups, 1 on each side. And that gives rise to a ring now which is fused together with 2 rings. So the maleic anhydride part and the diene part. Or you could do double bonds conjugated with ketones. And notice this one actually is symmetric. There are 2 double bonds. I've shown reaction of 1 on one side, but if you actually react this with a lot of butadiene and let it go longer, it can actually react on both sides. So it can react on that double bond as well to make a 3rd ring over here. So there are lots of possibilities that we have. You can see we can start taking relatively simple starting materials and start building up more complex structures, all in one step. It is a one-step reaction. All the bonds are being formed and broken at the same time. So we have in the transition state is a cyclic transition state, and I've just shown the bonds that are breaking and forming all in sort of dashed lines here. So the 2 new bonds which are forming, those are the new single bonds. So the original pi bond, let me just draw where the original double bonds were. There are the original double bonds. And as this changes, the electrons flow here to make that single bond. That pushes these electrons down to form the new double bond that's in the product. And then these electrons flow to form the new single bond. So again, all this happens at once. So what's very important for this reaction to take place is that the diene, or the conjugated double bond, has to be in a very specific geometry. Only if it's in this, what we refer to as an S-cis conformation, where the single bond rotation between them is such that both double bonds are pointing in the same direction. only then can we have all the bonds being formed at once. Because if it's in this other conformation, this side of the dienophile can't reach to form a bond. Okay, and that's critically important. We see that if we disfavor this equilibrium and we favor the S-trans conformation, we see that that has a negative impact on success in this reaction. So here, for example, making it sterically crowded, putting groups on in the right places so that if it is in this particular conformation and you have large groups that bump into each other, that means the equilibrium for this conformation, you're going to have more of this S-trans conformation, and that reaction won't proceed through this Diels-Alder reaction because it can't adopt the right conformation. If it's unhindered, then it can. So just notice by changing the EZ geometry of the substituents on the double bond, here they're all Z, this one is Z, and then this one is Z. Okay, and we change that to the all E, or trans, double bonds. It can adopt a conformation where those CH3 groups are not bumping into each other. And so this one would participate in the Diels-Alder reaction, whereas the other one will not. Okay? The best, by far, the best substrate for Diels-Alder reactions are this molecule here, cyclopentadiene, or things that are constrained to be in that ideal conformation. Those are going to be best, and this is one that is particularly good because, not only because the double bond is in the right conformation, the S-cis conformation for the two double bonds, right? But it also has some strain associated with it because in a 5-member ring, the bond angles aren't quite optimal. So, you know, an sp2 hybridized carbon would have 120-degree bond angles, right? Well, that's being compressed more than 120-degree bond angles in that 5-member ring. And so what that does is it provides some strain energy to that molecule. So that actually makes it a little more reactive. And so it wants to alleviate that strain, and by doing so, it does Diels-Alder reactions very well. Notice when we use this molecule for a Diels-Alder reaction, I'll just take just a simple alkene here. And if we form the bond here to the ends of the diene, push the electrons here, and then these electrons would go to this other new forming bond, what would that look like? Well, it's a cyclohexene. That's always the product of a Diels-Alder reaction. So there's the cyclohexene product, but there's also this CH2 group right there bridging the two N carbons. So that's going to be here in the middle. So these are the N carbons of the diene, and so there has to be a CH2 group bridging that. Okay, it's a bicyclo molecule. If you look on it from the side view, it looks more like that. And I have a number of drawings that show this, using this as a diene for Diels-Alder chemistry. Okay, so get used to viewing those three-dimensionally. It'll help out a lot. Okay, this is a visualization of that Diels-Alder reaction. In this case, we're taking cyclopentadiene again with a bridging CH2 between the ends of the double bond. And then the other double bond that we're reacting with is maleic anhydride. It has the two electron withdrawing groups, but then it's also in a ring because of the oxygen. That's why you see the oxygens in the red here. Notice as these two reacting partners come together, the diene now, the two carbons on the end of the diene go from sp2 to sp3 hybridized. And the double bond ends up in the middle between the two double bonds that started out as the diene. The dienophile also has a double bond. As it forms the bonds, it becomes sp3 hybridized as those new carbon-carbon bonds form. And this happens again all at once, happening at the same time. All the electrons in this six electron system, these three pi bonds, are all flowing at the same time. And it's only because that's conjugated, that diene is conjugated, and you can form that double bond between here and the end. That's why the reaction works. If those double bonds were just isolated double bonds, it would not work like this. Okay, so one of the nice features of this reaction, since we're forming all bonds at once, the reaction is stereospecific. And by that I mean that if we have, here I'm focusing on the dienophile partner, not the diene, I've just used simply butadiene in this example. But notice, if we have groups that are cis to each other on this double bond, and we carry out the reaction, those groups end up on the same side of the ring of that six-member ring. So we start with a cis double bond, and we end up with a cis substitution on the cyclohexane. Okay. If we change the stereochemistry, now we have the trans double bond here. I'll just throw the hydrogens into highlight. What happens is that the groups now end up trans in the product. That's the exclusive stereochemistry of the product. Okay, so the geometry or stereochemistry of the dienophile double bond translates directly to the stereochemistry of the product. That's why we refer to that as a stereospecific reaction. It's not a mixture. You don't get a selectivity of one stereoisomer over the other. The stereochemistry you start with translates it all the way to the stereochemistry of the product. And again, that's a result of all of these bonds forming at one time. So if you're only forming one carbon-carbon bond at once and then breaking pi bonds, then you'd have rotations before the second side or the ring closed. You wouldn't expect this kind of specific reaction. Okay, so knowing that dienophile geometry or stereochemistry is important in thinking about what the product will be. Here's an example, and I've shown the transition state a little bit on how these things are coming together. Here's another example using cyclopentadiene with a trans double bond. In this case, these groups happen to be the same. I have a CO2CH3 or an ester group here and an ester group here. Those end up in the product. So notice again, I'm starting with a trans double bond, and I end up with the trans substitution for those two groups in the product. Okay. Notice also what happens with cyclopentadiene. Okay, here's the cyclopentadiene. Again, it has this CH2 group, which connects the ends of those two double bonds, and that ends up here in the product. And if you look at the more three-dimensional drawing, you'll see there's the CH2 group, and here's our substituents that were on the original diene in a trans arrangement. Okay, and that can be explained if you look at how this approaches. Cyclopentadiene, because all of the atoms in cyclopentadiene are all in one plane, right? There's 4 sp2 carbons and then the CH2. Okay, all those are all in one plane. They have to be. And so it's a flat ring. And then this double bond is coming from one side or the other of that face. I just happen to draw it coming from the bottom because it's easier for me. And we have the two substituents now approaching trans. So notice, let me just clean that up a little bit. Notice those substituents and the groups related on the cyclopentane ring. So there should be a hydrogen coming out here that I haven't drawn and a hydrogen going back here. Okay. Notice those dotted lines, as those lines are forming, what is the relative relationship between these groups and the groups on the cyclopentadiene? Okay. Besides the 4 carbons that I've outlined with the blue bonds here, the orientation of the hydrogen with this group, or this CH2 group that's bridging with that group. Okay. As you bring these molecules together, the ends, all of those ends that are joining are becoming sp3 hybridized. So those 4 carbons in the product, right? Here's the 2 from the cyclopentadiene, and here's the 2 from the dienophile. Notice the orientation of the groups. If you look at this from the top, that's the drawing I've drawn here is the 6-membered ring. The CH2 comes up, and the H is going to go down, actually out. And notice here, the CH2 up is on the same side as this group and opposite side of that group. And hopefully you can see that here. The CH2 is going in that direction. This is going back, and there's a hydrogen there. So this and this end up on the same side. This and this hydrogen end up on the same side. Okay, can you see that? Sometimes it's hard without a real good three-dimensional model. The same thing here. I'll just draw the hydrogen back there. Notice this hydrogen is pointed to the back underneath that cyclopentadiene. This group is coming out away from it. And so this group and the CH2 should be on the same side. That hydrogen and that hydrogen should be on the same side. Okay, and that's where they end up. Hydrogen down, ester up, CH2 up. Okay? We're going to see some more examples of this. So if you're not quite seeing it now, we'll be seeing this over and over again. Okay, there's another observation we make in this reaction. So I showed you the trans dienophile, and on this slide I'm showing you the reaction with the cis dienophile. Okay, and now here's the difference. In the previous case, I had an electron withdrawing group. Actually, let me just back up one slide. Notice I have an electron withdrawing group on either end, but they're trans to each other. Okay? So one of them is sitting underneath this cyclopentadiene double bond system, and the other one is pointing out, away from that cyclopentadiene pi system. Okay? So it doesn't matter which way I draw this. So if I were to just flip that over, one would still be under and one would still be out. Okay? But take a look at the example on the next slide where I have the cis double bond. All I've done is change the stereochemistry of the double bond. And now both of these ester groups are pointing in one direction. So now we have a possibility of forming 2 different diastereomers in this reaction. Okay. The product, relative, again, so if you look at all these groups on the cyclopentadiene, okay, and we have hydrogens here, relative to the group on the diene versus the dienophile, there are 2 products, one in which the CH2 group is on the same side of the 6-membered ring as the 2 esters. Okay, that's shown in this top 3-dimensional drawing. All right, the hydrogens that were here are sleeping here and back. Okay, so can you visualize that? The other diastereomer now is if that CH2 group is still up in the ring, but the 2 ester groups are pointing down, as opposed to out. So notice those are not enantiomers, those are diastereomers. So in this case, the CH2 is still coming up, but now these groups are opposite. This reaction actually, although sometimes we see a mixture of these 2 diastereomers formed, there is a preference, and there's a major product. And so here are the 2 transition states where those, as you visualize these groups coming together, to get the product on top, where the CH2 group and the other groups on the dienophile are on the same side, that means those groups have to be pointing out. Okay, so this comes together to give the product on the top. All right. If I take this dienophile and flip it over, that's the structure you would see on the right. If they come together from the other face of the dienophile, that would put these groups pointed underneath the diene portion and lead to the product on the bottom. So which do you think would be the major product? The left one. How many people agree with that? Okay, pretty good agreement actually. Now, why do you think it's the left one? Sterically hindered. And that would be a good guess. You would think that this one is less sterically hindered because these groups are out more in the open, and that one is more sterically crowded. But there are two aspects to selectivity and transition state energy. One is sterics. Sterics certainly can play a role. The other is the electronics and how stable you can make the electronic system. It actually turns out this goes against your intuition on sterics. The bottom structure of this transition state on the right is the lowest energy one, not because of steric reasons, but for some other reasons. And so this is the major product, this one on the bottom. Okay. By the way, we have some terms. Here's some more terms for you to remember, and that is when we do a Diels-Alder reaction where the groups are pointing out, away from the diene. Okay. We refer to this as the exo transition state. And when they're pointing underneath, this is called the endo transition state. Endo, under, it's kind of easy to remember that way. Endo. An endo, when you have these electron withdrawing groups, endo is the preferred one. By the way, if these groups weren't there, if those were not CO double bonds on those carbons, and they were just alkanes or something, the sterics would be the important feature. So this is true for most of the cases where we have all these electron withdrawing groups. That provides a different aspect for the electronics. And we'll go over that and explain that a little bit. But the endo, in general, since we're usually using some electron withdrawing groups, the endo product, or the product of the endo transition state, is a major product. Okay? And I hope you're asking yourself now, well, why? Why is it not sterics being the most important thing? In order to really understand that, we have to talk a little bit about how these orbitals interact in the reaction. Okay, so I'm going to pull out a little bit of molecular orbital theory. Remember, molecular orbital theory says orbitals don't exist necessarily on individual atoms, but are spread out over the molecule. And it's a different way to look at it. And fortunately, we don't need to look at every electron in the molecule. We can focus just on the pi bonds. So if you take a look at the molecular orbital, or how we describe, this is how the mathematics describes the molecular orbitals for a single double bond. So this is ethene, CH2, CH2. Sorry, you can't see the double bond in between there. This is essentially an energy diagram describing the bonding in ethene. So if you think about a carbon atom here and a carbon atom here with a p orbital and a p orbital, and you bring them together, they form, with one electron each, they form two molecular orbitals. A pi bonding orbital, this is what we refer to as the bonding orbital, and what we call a pi star, or a anti-bonding orbital. Okay? Since we start with two, and when the mathematics combines them together, we end up with two molecular orbitals. Notice the electrons pair up energetically in what we call the bonding orbital. Okay? The anti-bonding orbital is empty. We don't put electrons in there. And also notice what happens is on a p orbital, on one lobe we have, say, a plus sign and a minus sign. That's how the mathematics describes it. Actually, I've shaded this dark with a plus and minus. And so notice they match in that bonding orbital. And as we go to the next higher orbital up, there's what we call a node in between. They don't match from one side to the other. So what that means is when these signs don't match, there's no interaction between those in that particular orbital. That's what that means. Well, no significant bonding interaction. So this is the simplest pi bond you can look at, a single double bond between two carbons. We have a bonding orbital and a non-bonding orbital, and it's That describes what we see in terms of its reaction. So what happens if that has to react with another pi bond, like in the deals all the reaction, this is coming together with a diene. We have to consider which of these signed orbitals are interacting, because they have to match. Another term for you, the highest energy of the bonding orbitals we call the highest occupied molecular orbital, and the lowest energy unoccupied orbital is the lowest unoccupied molecular orbital. We just refer to this as LUMO and HOMO to describe those. In a simple ethene, there's only two. In a diene, there's two additional ones. So there's a total of 4, because we're bringing 4 p orbitals together. And I hope you're still with me. Let's take a look at butadiene now, compared to this. So here's butadiene. Essentially what we have are 4 p orbitals that have to come together and mix and mathematically mix into 4 molecular orbitals at varying energies. And so what happens again is you pair up into the lower energy orbitals. These are bonding orbitals. And then we have anti-bonding orbitals. The bonding orbitals are not necessarily the same. And it's a little bit abstract because we're not really describing individual pi bonds or anything. We're talking about the whole electron density. And you'll notice that the lowest energy bonding orbital, if you look at the mathematical symmetry of the signs of those 4 p orbitals that make it up, notice they're all on the same sign across the board. One of the aspects to molecular orbitals is as you go up in energy, stepwise through each of the molecular orbitals, you have to increase the number of nodes between these. So notice, if I look at this orbital, which is the highest occupied molecular orbital, that's the highest energy orbital which has electrons in it. Notice the signs are opposite for the 2 on the left and the 2 on the right. So there's a node, what we call a node in between. One node. So we go from 0 nodes to 1 node. And then as you go up this energy, notice there are 2 nodes now. These ones have the same sign. And then at the highest one, there's 3 nodes. Okay, the sign alternates every single orbital. What's important to recognize, and not that I'm going to have you be able to draw these and construct all these orbitals, what I want you to recognize is that when we do reactions between 2 different molecules, we have to react the highest occupied molecular orbital of one with the lowest unoccupied molecular orbital of the other. And so thinking about how these things come together in this Diels-Alder reaction, it's useful to consider that since this is the electron-rich partner, it's the HOMO orbital that's going to react with the LUMO of the dienophile. So this is the picture we need to think about. And if you're not totally confused yet, let's take a look at both of them together. These are the same pictures. I've just put them side by side. And what I've pointed out here is that I've kept the picture for the orbitals, our more pictorial view of the reacting ones. So here in the diene, so this would be butadiene. Okay. This is the orbital picture we're looking at. Okay. On one end, let's say we have plus, plus, minus, minus. Minus, minus, plus, plus. So that represents the 4 carbons in a row. Okay, I've just drawn it out in a row. That highest occupied molecular orbital has to react with this orbital of our double bond, the lowest unoccupied molecular orbital. And one thing I want you to notice from we're reacting on the N carbons of butadiene and the N carbons of the double bond, right? That's the carbons that are all coming together to form bonds. So here's the real crux of this. If you look at one side of this, you have a plus sign and a minus sign. They're not the same on either end of the reacting orbital for the diene. And the dienophile, we have a plus sign and a minus sign on either end of the dienophile, which is reacting. Those match. Okay? However you orient that, they have to be opposite. If we have the dienophile which has plus and plus on the same side, it doesn't match with this orbital being plus minus. Okay? This actually is important also for this reaction. So I actually have those drawn out on the molecules to give you a little bit better picture. So if we take a look at this now in the way these might come together, in blue is our butadiene. So there's actually, if you think about those two double bonds there, and we have a double bond coming together. And notice, instead of drawing it out flat like this, I've put it more in alignment with, so that would be the picture. Oh, my drum's terrible. Remember we had this with one node in it, and that node is right there. Notice plus, minus, minus, plus on the top, minus, minus, plus, plus, or shaded. The shading gives you the signs on the bottom. As this group approaches, the shading or not shaded parts of the orbitals match with the diene. And that's why the bonds can form properly. So that mathematical symmetry that we calculate using quantum mechanics for what we describe as the molecular orbitals actually explains or gives us a predictive power on how those come together. So notice here, there's a minus, that would be a minus. A clear shading and a clear shading, those match. Here it's dark shaded and dark shaded, those match as they come together. So the two ends match. Allows us to make bonds. So that's an orbital description, actually, of how this reaction takes place or comes together. But now, how does that explain why we want the electron withdrawing group oriented underneath? Well, if you really think about these pi bonds as being these orbitals, notice also there's a sign for the orbital here. On the bottom of this diene on this side, let's say it's minus and minus. Okay? We're not forming a bond to these in the back, but all of this is part of the whole system. So if I have an electron withdrawing group, let's say I have hydrogen here, and I have a CO here. Look at that CO. What is a CO double bond? It's also a pi system. Okay. It's also a pi system, and it happens to be, this is the highest occupied molecular orbital of the diene. This is the LUMO, lowest unoccupied molecular orbital of the dienophile. And notice, if we extend this now further, what this would look like on the CO double bond, or a CN double bond, or triple bond, or anything that has that kind of pi bond. Notice, it's unshaded and unshaded. Guess what? Not that it forms a bond there, but there is some stabilization of the transition state. It's a lower energy transition state if this can overlap during the reaction and then not form a bond at the end. So it's just helping the energy of the transition state be lower so it's faster to form. That's the reason why electron withdrawing groups want to be endo instead of exo. And I have those drawn on the next slide as well. Yeah, both of them. So here would be the difference. Endo, in the endo transition state, when you have it like a CO double bond or something like that, versus the exo transition state. This provides an additional interaction, even though it's more sterically crowded. it is still lower in energy because of the electronic system involved. It helps to stabilize. And this is what we call a secondary orbital overlap. Meaning it's not forming a bond, but it's providing stabilization energy because there's interaction in the transition state. So after all that, if I would have just said there's secondary orbital overlap without going through this description of molecular orbitals, it wouldn't have made any sense to you. It probably still doesn't make much sense to you, but now that you know that mathematically we have to combine the right orbitals at the right energy to get this reaction to occur, that's why all the signs match to be able to provide a low energy transition state. The bottom line is, if you have an electron withdrawing group, you want it preferentially underneath the diene instead of pointed out. Okay? Anything that has this additional pi bond or double bond character, either CO, CN, even a CC bond, that can all help in this reaction. Okay? So endo, again, preferred with electron withdrawing groups that has a pi bond. Here are some other examples. And notice, you don't have to have electron withdrawing groups on both ends. Here's a dienophile, cis and trans, where we have just an alkyl for an electron withdrawing group. There you can have multiple possibilities. Okay. In the top case, electron withdrawing group underneath also has the CH3 underneath. So notice you get a trans product. I'm sorry, a cis product at the end. There's a 10. Okay. Cis. In the endo transition state, endo referring to the group that has the additional pi bond, endo transition state is the favored one. You'll get that product. Now, there's nothing else on the diene to compare it to relatively, so you wouldn't be able to see it very easily. I'll show you cyclopentadiene in a moment, and other groups as well. If you use the trans one, right, now you have one group pointing out and one group pointing under. There's a difference which one you point under and which one you point out. It's going to be the one with the CO double bond in this case that gets pointed under. Okay? Now let's look at some more examples of this with more group signs. So I added this slide. This wasn't in the handout, but I've just drawn generically a diene and a dienophile with a CO double bond. And there's the product. And let's say we have different substituents, A, B, C, and D, on the ends of the diene. Okay? Where do they end up at in the product? Relative to this group. Okay, this group here ends up here, and I've drawn it down. Again, I'm thinking about the transition state, which I'll show you more details in a second, of it coming underneath the diene. Notice the orientation of things that I've labeled A, B, C, D. The A and B has to be on the top here. Okay, one of those has to be A, one B, and down here one C and one D. Okay. Which group goes where and why? One thing I should mention, notice in here I just have simply hydrogens, but there could be substituents there too. On the inner carbons of the diene that's reacting, doesn't really matter much because those end up still sp2 in the product. There's no issue of up or down on the ring or stereochemistry. So that's the good thing. Groups here just hang out where that double bond is. And you don't have to worry about up or down relative to groups here. All right? So let me just say that in this case, what ends up on the same side as this group from the dienophile, this CO double bond, the groups which end up on the same side are the ones pointing out away from the diene, and the groups pointing in end up on opposite sides. So in this case, the stereochemistry of the product, if it goes the endo transition state, the major product should be the one where B is up and A is down, C is up and D is down. Okay, and I'll show you the transition state to show how all those relationships go again. Again, this is the major product from the endo transition state as they come together. All right, so how many people have difficulty seeing how the stereochemistry relates from here to there? One rule of thumb, if you always think about the dienophile coming underneath the diene, like the way I've been drawing it, of course you could bring it from the top too, and that would flip everything 180 degrees. But if you always think about this coming from the bottom and always draw that group down, that would be underneath the diene. One way to remember is things pointing out end up on the same side as that group, down, and pointing in end up up. All right, so let's look at this as they come together. There's the transition state. Let me put in the groups. Let me draw in those groups then. So notice on the end of this, I'll just draw the hydrogen here. There's the hydrogen also on that group. Hydrogen, guess I should draw it in the right orientation. Hydrogen coming out, and then the CO double bond underneath or endo. Okay? And this diene, since it's flat, we have groups pointing straight out from there, and we have groups pointing more inwards. So what I've labeled up there is A, B, C, D. Right? So as this bond forms, okay, this is going to be up, this is going to be down, the C is going to be up, and the D is going to be down as those become sp3 hybridized. Okay? So this, as this group shifts up as it becomes sp3 hybridized, because this bond is forming from the bottom. Same thing with B. B shifts up as the bond is being formed from the bottom. So that's going to be up, and that's going to be down. Okay, so looking at this in this three-dimensional conformation, does that help you visualize it a little better? I hope.
So it just rotates.
Right, so as this becomes sp3, it goes like that. So C goes up, D kind of goes down, this group is down, this group is up. When you look then from the six-membered ring, looking from that direction on this six-membered ring that's formed, and the way I've drawn it flat here, again, this would be C up, D down, B up, A down. Okay? Remember, now this is butadiene that I've drawn generic groups on. If it were cyclopentadiene, okay, what we have pointing out is hydrogens, and what we have pointing inward is this CH2 bridge. Okay, so the CH2 bridge, in this case, would be here, it would go upwards. The hydrogens out would go down. Okay. Here's an example of another diene. One of these has a trans double bond, and the other one has a cis double bond. But if we take the diene part and orient them in the right direction, that transition state would look like I've shown here. And so now what I have, there's a lot of things going on in this reaction. I have a substituent here and here in the diene. And now I have a CH3 versus an electron withdrawing group in the trans orientation or stereochemistry of the dienophile. As those come together, I want to think about this diene, as I've drawn there, with the other double bond underneath it, okay? And I want to point the electron withdrawing group underneath, as I've shown up there. And since that is trans to a CH3, I have to put the CH3 pointing out. So that's my terrible drawing, but what I've drawn a little better above it. And you can see that, and I've shown the bonds forming here. And then the groups that are on the diene, notice on the bottom of this diene that I've shown here, I have CH3 trans and H cis to this. Now that I've written all over. Okay, this CH3, and what I haven't drawn here is the hydrogen here and the hydrogen there. Okay, I've drawn everything on here except the one hydrogen, just for room. That hydrogen is pointing inward. Okay, so I left it out just for clarity so that you can see. So we have this CH3 pointing outwards and this CH3 pointing inward. So when you do the reaction, on this part of the molecule, one's going to go up and one's down. That's what I've drawn on the product. This CH3 went up, and that CH3 went down on the ends of where the double bond was. The double bonds go down. Okay. This group now is going to be down. So I've drawn that down here. This group, since it's pointing out, along with that hydrogen, that's going to be up. And so if you think about how that all comes together, you should be able to predict how those two would come and form this product. So what I'm talking about is, of course, all the relative stereochemistry. That is the orientation of this versus this versus this versus this. Not the absolute enantiomer. Actually, we don't have a way to control that in these reactions because there's nothing chiral to start with. Okay? I've drawn one enantiomeric possibility for the transition state. If I take this double bond and bring it from the top of that diene, I get the exact same product but the mirror image. Relatively, cis and trans, they'll all be the same. But if you flip every single stereocenter, that will be from the transition state where this comes from the top. Okay, so what's important here is we're talking about the relative cis and trans relationships between the substituents on the cyclohexene ring in the end. Yeah, here's one with cyclopentadiene. This shows you also the same kind of thing, the orientations of these groups. The orientations of these groups, and notice if we're using cyclopentadiene, it's the two hydrogens pointing out away from the diene part, okay, and a CH2 group pointing in. So the way I always draw this, to keep it straight, the diene on top, the double bond coming from the bottom, the electron withdrawing group pointing underneath, that ends up down. And so I always start with that down, and the cyclohexene ring here. And then I look at the groups here. So I have a CH2 group inward with cyclopentadiene, so that comes up. Opposite side. Okay. So again, electron withdrawing group opposite from the CH2. It'll end up on the same side as the hydrogens next to it. Okay, so that's the, is that all I have? Yeah. That's the stereochemistry aspects of the Diels-Alder reaction. You should take a look at the practice problems in the book. Hopefully the LearnSmart, I haven't seen what all the LearnSmart had you do with this, or how well it's drawn for you. But hopefully that if you go through those, you'll see how all that stereochemistry turns out. Okay.